is actually here 80 to 100% reads, because that's where the typical file system workloads are. We'll actually show that for most typical file system workloads, there's 80%, around 80% reads and only 20% writes. Here you can see that for this real area where the file system works, we have overheads of less than 5% for both modes. But now there's a problem. Postmark is not a real file system benchmark. I mean, it's not a benchmark for real files in real file systems. In your file system, you don't have 20,000 small files. You have lots of MP3s, lots of videos, and lots of documents with megabytes of sizes, and then also a lot of small files. So we need to simulate what the behavior, test the behavior in a real life file system. And for that, we simulated a file system using the log normal model. People have found that the file size distribution in a file system follows the log normal model. And we created a file system with 20,000 files using these parameters. And because people these days keep a lot of movies, videos in their website, in their disk, we threw in a bunch of gigabyte-sized files. And we also wanted to use data from real systems, the workload. So we used information from these 5 studies. The first 2 are instructional lab and research labs, with very little writes, less than 3% write in both cases. The next are corporate and engineering section workloads from a recent paper, and these are somehow more, but still less than 20% writes in both cases. And finally, there is this weird worst possible case workload, and it has 82% writes, only 18% reads. This is a really weird behavior, but that's the worst possible case people can have. So now we wanted to see the behavior with typical file system workloads and how much overhead we have. So on the left side of the screen, we have the config disk model, where we stored the files on the disk. So here, and on the right side, we have the RAM disk buffered case, and we varied the number of transactions from I think 20,000, 30,000, 40,000, 50,000, and so on, all the way to 200,000 transactions. So for the first 2 workloads, the INS and REST workloads, you see that the overheads are quite low. Both of these are read intensive. Most of the transactions are reads. So naturally, we are only recording the writes to the provenance chain, so the overheads are low. The overheads are less than 5% here, and here it's less than 1%. How about the next one? The CIFS Corp and CIFS Eng. Well, here, if you recall the previous slide, we had 15 to 17% write transactions in these 2 workloads. But still, we have overheads of around 13% here, and maybe less than 3% on this RAM disk buffered case. These are quite low. Even in the worst possible case, in the EECS workload, we have a lot of unrealistically high number of write transactions, 82%. Overhead is naturally high, but we still have around 35% here and less than 7% with the RAM disk optimization. And I also have this slide where we show that even if you record the reads as well, not just the writes, we also tested what happens when we record all the transactions, the reads as well. Even in that case, the overheads are still between 12% to 16%. So in this way, in these applications, through this experience, we showed that it's possible to record all the file system activity and in a secure manner, but still pay a very low cost. If you go back to the previous slide, most of the typical file systems behave like these 4 curves, because most of in typical file system workloads, we have more reads than writes, and the read-write balance is around 80-20. So for all of these cases, typically our overhead would be in the range of 1% to 11%, or maybe 13% here. So now we have, so in this talk I have described schemes for providing a generic scheme for making data history trustworthy in file systems. So that's one way of making data history secure. In the rest, or in related research, which I'm not going to present today, but in related research, we have looked into other application-specific areas as well. And there we have looked into the history integrity problem in databases. That is how we can preserve database history, the history of transactions in a database, and do that with as low as overhead as possible. So we have developed a solution using trustworthy warrant devices, and we incur only 1 to 3% overhead for TPCC benchmarks in databases. And finally, we have also looked into how we can provide history integrity assurances for cloud computing. So now, what can we do in future? That's what we have done so far, but what lies ahead? Now, we are adding more and more power, packing more power into our machines, adding more processing power, adding more storage. Now you can buy a terabyte disk for what, $100 or less than $100. Maybe in 5 years from now, you can buy a petabyte disk for $100. So we have enough space to store the history as much as we want. And we also have enough processing power to process a lot of things. So what can we do if we given enough technology? Well, one thing we can do is to generalize all these things. So we have provenance, we have versioning, snapshots, all these things that are basically a way of representing history. We can call this property remembrance, and we can make different parts of our computing system remember their past. In this work, I just talked about files, but what if your hard disk could tell what it stored in the past? What if your program variables could say, or your program memory could recall what it contained 5 minutes ago? Wouldn't it be nice to have a knob on your machine and go back 5 minutes ahead just by turning the knob? If different parts of your system remembered all their histories, your applications remembered what their state was 5 minutes ago, and your operating system knew, your file system knew, if we could have this common remembrance property, we could do a lot of these cool things. And because this is a security seminar, I'll just talk about what it means for security. We can have interesting things. For example, we can use it for authentication. Rather than using these other factors such as what you have, what you know, and what you are, these 3 factors of authentication, we could have used what you remember. So if someone comes in and tries to get through a door, you can just ask him, tell me what you did inside yesterday. If they can tell you that, then you let them in. So you can apply the same idea for applications or websites or different parts of your computer. Use this for authentication. You can also have flexible authentication, flexible security policies, that is, use the knowledge of the past to compute complete policy compliance, and also you can check information flow and apply information flow policies based on not the current value but the past values of the variable. So, in summary, we can claim here that we can have secure provenance at a low cost. The message you should take from this talk is that yes, we can have security integrity assurances for data history, data provenance, file provenance, and we can have that, but yet have an efficient working file system. In this work, we show that for most real-life workloads, the overheads are really low. These are between 1% and 15% for typical file system workloads. And if you are interested to learn more or to read the papers, we published a paper in Unix Fast 2009 and also have a journal submission right now. If you want to read them, you can just go to this website, tinyurl.com/secprov, and you'll see the performance numbers from there as well as the papers. So that's the end of my talk. So now I'd like to have any questions if you have.
Are there any questions?
So let me give you one question. Why can't we take the same technique we used in file systems, and why can't we use it for databases? right? I said that